Hey there, awesome physics students. Let's talk about how to compute torque with an actual example. Now, in this example, not only are we going to talk about how this example works, but we're also going to show you some of the procedures and conventions that you use in solving all torque problems. Okay, so here's the situation. I've tried to keep it very simple here. There's a rod that's 20 centimeters long, or 0.2 meters, and there's an axis right in the middle of it that it's free to rotate. That axis is labeled A, and so that's in the middle. So this is 10 centimeters here, and this is 10 centimeters here. And there's a variety of different forces. There's a 20 Newton force at an angle of 30 degrees. There's a 50 Newton force at some unknown angle that's acting at the axis of rotation. That might be a problem. There's a 15 Newton force acting to the left. There's a 30 Newton force acting straight up. And then there's a 100 Newton force acting at an angle of 15 degrees, but it's only acting 5 centimeters from the axis of rotation. So what we want to do here is add up all of the torques on this about the axis A. The first step in any of these problems is always to draw the free body diagram with the forces drawn where they act. So I've already done that here. That's why it's important to note which way the forces point, of course, as always, but also where do they interact with the object. And you want to clearly label your axis of rotation, which I've done here too. The other thing you always want to do is identify a positive direction of rotation. And by convention, our positive direction of rotation is counterclockwise, is positive. Okay, that means clockwise is negative. So as you see it, this direction is going to be positive, and then this direction will be negative. All right, so let's go ahead and get started. We want to add up all the torques, so I'm going to sum all of the torques. I'm using this letter sigma to denote the sum, and I'm doing it about the axis A. And the reason I have to label which axis I'm using to sum the torques is because I will get a different answer if I use a different axis, because remember R is in the equation for torque, and that R goes from the axis of rotation to the place where the force acts. So while I'm talking about that, let's go ahead and talk about the torque equation here. This is mostly we're going to use F perpendicular times R. So this is the part of the force that's perpendicular to the R vector, and remember the R vector goes from the axis of rotation to where the force acts. We can also use FR sine theta, where F and R are the magnitudes of those vectors, and then sine theta is the angle. Theta is the angle between the R vector and the F vector. So we'll use either one of these two in this case. So let's go ahead and get started. We're going to get one torque for each force. So we're just going to go force by force by force and add up each of these torques, and we're going to get a term here for each torque. So let's go ahead and get started. For this 20 Newton force, I'm going to use this equation here. So I need to find the part of the force that's perpendicular to the R vector. First, let me draw the R vector. That goes from the axis of rotation to where the force acts. So here's my R vector. And I want the part of the force that's perpendicular. So there's the part here that's parallel to R, and then there's a part here that's perpendicular. So I want that. That's adjacent to the angle 30 degrees. And so I want the cosine of that. So my perpendicular force is going to be 20 newtons times cosine of 30 degrees. That's going to be the perpendicular part of the force. And then I'm going to multiply that by the magnitude of my R vector for this force. And that's going to be half of the 0.2 newtons. So that's going to be 0.1 meters. Okay. Finally, I want to think about whether this one is positive or negative. Well, the axis of rotation is here, so I put my thumb there and I can curl my fingers of my right hand in the direction of rotation, and it's going to be counterclockwise, so this is going to be a positive torque. Okay, so this one's done. Now let's move on to the 50 Newton one. That one has, I'm going to use this expression here, FR sine theta, but for this one, so F is clearly 50 newtons. R goes from the axis to where the force acts. That's here to here. Notice that that is 0, right? And so it doesn't actually matter what the angle is. I don't even need to know theta because R is 0. And if you think about this, makes sense. This 50 Newton force is not going to cause this object to change its rotational state, it's not going to cause any rotation in the common phrase that we would use about the axis. So that one causes no torque about A. All right. Then I want to add in the next torque here. So I go to this force. This is a 15 Newton force. So in this case, my R vector goes from the axis to the point where the force acts, and that's going to be there. And so the angle between these is 90 degrees. And so I can use this equation here. So that's going to be F, which is 15 newtons, times R, which is 0.1 meters. And then the angle there is sine, that's 90 degrees. Sine of 90 is 1. So oftentimes once you get good at this, you'll just leave that term off. I could have used this one and noted that F and R are totally perpendicular to each other and just skip the angle, but I wanted to show you how to use both of these. Finally, I need to think about, is this positive or negative? That's going to cause rotation this way, which is clockwise. So this is a negative torque, and I need to add the negative by hand. So I have to think about this each time. All right, let's keep going. So I've done this one and this one. Now let's go to this one. So let's add in the 30 Newton force. And that one, R goes from here to here. It's the same R as the other one. And note that those two are parallel to each other, right? They're anti-parallel. So the angle between those is 180 degrees because they're anti-parallel. So I'm going to have sine of 180 here. Sine of 180 is 0. So again, intuitively, this force, this 30 Newton force, is not going to cause clockwise or counterclockwise rotations around the point A. It produces no torque, okay? So this is going to be 0, but I've written it out here anyway. All right. Finally, let's do this 100 Newton force. And this one is the biggest force, so I'd expect this one to be the biggest torque, right? So let's see about that. So we're going to have, I'm going to use this formula here again, FR sine theta. So let me take 100 newtons times R goes from here to here, points down like that. And then, so the angle between those two is 15 degrees. The R vector is 5 centimeters or 0.05 meters. And then the angle between them is 15 degrees. So I have sine of 15 degrees. And then I need to think about whether this causes a clockwise or counterclockwise rotations. This is going to tend to cause, if I think about the perpendicular part of that, that's this way. That's going to cause counterclockwise rotation. So this is going to be a positive torque here. All right. So now I can go ahead and compute these. Of course, this is 0 and this is 0 because if you multiply them, you get 0. So I only have this term, and this term. If I take this one, that gives me 1.73, and the unit for this is newtons times meters, and I don't simplify those to any other unit. Notice that this is the same unit as energy, joules. However, it's not an energy unit, so do not simplify it to joules. Leave it as newtons meters. That's a unit of torque. Okay, that's a positive 1.73. This one is a negative 1.5 Newton meters. And then this last one will be, if I multiply that one together, I get a positive 1.29 Newton meters, because that is a positive torque. And when I add up all these together, I get positive 1.52 Newton meters. And so at the end of this, you might think, okay, I got my number. What does that tell me? Well, first of all, is this positive or negative? Well, according to this, it's positive, which is telling us that if I left this thing at rest and then I applied all these forces, this thing will have an angular acceleration in the positive direction. So it's going to begin to rotate counterclockwise if it's beginning from rest. This also tells me that a couple of other things to notice. Notice that even though this 100 Newton force is the biggest force by far, its torque is about the same as the others. It's not terribly bigger. In fact, it's the smallest. And why is that? Well, for one, it's got the smallest distance from the axis of rotation, and that comes into play here. The other thing is that Sine is maximum at 90 degrees when the things are perpendicular. As they become more parallel, that sine term gets smaller and smaller. And sine, when they're totally parallel or anti-parallel, sine of that is 0. And so sine of 15 degrees is a small angle. The sine of that is rather small. The perpendicular part of this force is actually quite small. So there's not a lot of, this is not a very effective way to create torque on this object. You need to make it more perpendicular, and you need to make it apply it farther from the axis of rotation to get more torque out of that 100 Newton force. Okay, I think that's everything we want to talk about here. So hopefully this can clear some things up. We'll talk about some other examples in other videos.